All right. So, okay. So today my plan is to discuss tutorial 4 that again is already like done and you have the solutions for it. Answers, not the solution. So my plan is to discuss that tutorial 4. Okay. So this is based on Chandrasekhar limit, radiation thermodynamics and black hole thermodynamics. Um, and I think in comparison to the other uh, tutorials that you have done, I think this is relatively quite simple. It has very simple basic tricks to be used. So we'll see all of that. Okay, so let's start. So this is your assignment. I'll just copy first question. Okay, here we have it. The degeneracy pressure of an ultra-relativistic Fermi gas in 3 dimensions may be written as P is approximately equal to rho raised to the power of n. So we have to find the relation of pressure in terms of the density, right? So what is the value of n? That's what they're asking. Mm, First, what we will do is we'll be writing rho in terms of kf. It's already done, but just to give you a brief reminder, what is rho? Rho is simply n by v, the number density divided by the volume, the number density of electrons or the particles. So this is just simply 1 by v into 2 into sum over all of k's. Uh, Maybe directly if we do it, we can say that all of k is less than kf, right? Into 1. Here we could have had that Fermi-Dirac function, but what we are doing is we are talking about absolute zero temperature. So in that case, the Fermi-Dirac function for k less than kf is 1, and for k greater than kf it's 0. So we can just write the summation over k less than kf. That's it. Why did I bring this 2 factor in? Because it's a fermion, so we are taking into account both the spins. So this is just 1 by v into 2 into what do we have here? Mm, 4 pi k square dk, where dk goes from 0 to kf. Oh, am I missing something? Am I missing? Yeah, in converting summation to an integral, I first have to make these changes as well. I'm converting this sum over k to an integral over this d cube k. So how do we convert this from sum over k? We have to the volume has to be multiplied divided by 2 pi the whole cube. This is in 3 dimensions, so that's what it will happen. If it was in 2 dimensions, you know that it will be a upon 2 pi the whole square. Or in 1 dimension, it would be just simply length scale, the length of the sample or whatever you are considering, divided by 2 pi. Integral d square k. This is integral dk. Here, because we are going to d cube k, so there will be a v divided by 2 pi the whole cube. Right. So just doing this here, rho is equal to 2 by v sum over k less than kf 1 is equal to 2 by v into v divided by 2 pi the whole cube, converting the summation to an integral d cube k. That's it. Into 1, which is d cube k itself, is equal to 2 by v. I don't need to write v anymore. It can be simply 1 upon 4 pi square, 4 pi cube, not 4 pi square, 4 pi cube into 4 pi k square dk. 2 by v into 4 pi k integral is done, k cube divided by 3, 0 to kf. What do we get here? Kf cube by 4 pi cube. I'm missing something. I'm getting 3 pi square. Kf cube by 3 pi square. Is it kf cube by 3 pi square or 6 pi square? I am not sure of the expression. It is 6, so I'm missing uh, a half term somewhere. Comes out to be kf cube by 6 pi square. What did I miss out? Two by the summation over this is correct. There's nothing wrong with this. I have 2 cube. Yeah. Um, I can't see an issue. Guys, can you point out an issue that happened here? The form is this only, but I'm missing a factor of half somewhere. So does anyone know where I missed a factor of half somewhere? Rho is directly proportional to kf cube. That's true, but it has to be 6 pi square. Um Taking a 2 here also is correct, right? It's number density. Obviously, I have to take a 2. So where did I go wrong? Can't figure out. D cube k has to be 4 pi k square dk. Mhm. Okay, so rho, what I got is kf cube by 3 pi square. Let's keep it at this right now. I'm missing a factor of half somewhere that I know of because in lecture it's not done in this way. So where exactly I can't figure out right now, but let's keep this because we don't need the exact constants here to get this answer. We just need the power dependency. So let's keep this at that only. And let's move on to calculating the pressure. If at all you guys know, understand where I missed the half, please tell me. Otherwise, I'm just moving on with calculating pressure. Pressure can be calculated by, you have this log expression. What is the expression exactly? This is the expression. You have an expression of this form. I'll just copy this here. So the most fundamental expression for calculating pressure is of this form, right? We have already derived this in class. This is for three-dimensional gas, right? So we already derived this in class, a gas trapped in 3 dimensions. Now we are in beta tends to infinity limit, which means temperature tends to zero limit. So in beta tends to infinity limit for epsilon j, which is greater than mu, e raised to the power of beta into mu minus epsilon j. What does this give you? When epsilon j is greater than mu, so this term is negative and beta tending to infinity, this will give me 0. So for epsilon j greater than mu, this summation will not give me any contribution. Only for epsilon j less than mu uh, will I get any contribution, and that contribution beta into mu minus epsilon j, and this contribution will be very large because beta is tending to infinity and mu is greater than epsilon j. In that case, this contribution is going to be very high and it will be much higher compared to 1, right? E raised to power beta of mu minus epsilon j is going to be much greater than 1. So I'll just ignore this 1 here, this 1 which I have here in this equation, that I'm going to ignore and simply write this as P is equal to 2 by beta V sum over J equal to 1 to infinity, basically all energy states. But now, because we know that we don't have to go for, till all energy states, the summation will be restricted to epsilon j less than mu. For all epsilon j which are less than mu, I'll restrict the summation to that. Uh, and one is something that we ignore, e raised to power of beta, this expression I'm talking about here. Uh, so it's e raised to the power of beta mu minus epsilon j. So log of that, log of something exponential is just that term in the exponential. So what I'll be getting is just simply beta of mu minus epsilon j. This is what I get because I've ignored this one. So this is just exponential and will come out of the log. So that's what I've done. This is what we get. Uh, at t equal to 0, by the way, mu is equal to mu f. So I'll just write mu f here. And epsilon j, because the question talks about ultra relativistic Fermi gas. So in that case, epsilon j is what? Someone tell me the expression. I'm seeing no interaction today at all. Guys, you guys can unmute and speak. Please speak up, unmuting yourself. Don't, because it becomes like more easier to understand whether you're getting what I'm saying or not. Otherwise, it's just me talking to myself. Uh, upon h bar k square, right? Okay, your microphone is not working. That's okay. Fine. MC square the whole square plus h bar k square. I hope I'm not missing out on the expression somehow. I hope that's the correct expression. Just let me check once. I think this is the correct expression. Yeah, so we have p square into c square, right? So my bad. So this is p square into c square. So h bar square k square into c square. This is my epsilon j, right? Now, given that it's an ultra relativistic limit, what does that mean? That means that h bar k, basically this term, this term is much greater than this term. H bar square k square c square is much greater than m square c raised to power 4. So basically h bar k is much greater than mc. This is my ultra relativistic limit. Therefore, I can just simply ignore the mc square part and I can simply write 2 by beta v sum over epsilon j less than mu beta of, this is mu f now, and mu f can also be written in terms of this. Mu f can be written as h bar square kf square c square plus mc square whole square. This is mu f. Mu f is this. This is the expression for mu f. So I will have two expressions here: h bar square kf square c square plus mc square the whole square minus square root of h bar square k square c square plus mc square the whole square. This is my expression. Now I will be ignoring the mass into c square part because it's the ultra relativistic limit. So what I get is 2 by beta v epsilon j less than mu beta into h bar kf c minus h bar k c. So anyway, I can just remove this beta. And now this summation basically was for all the energy values which are less than mu f. Mu is mu f in this case. So all the energy values which are less than mu f. So equivalently, it is a summation over all the k values which are less than kf. Again, the same logic. So 2 by v multiplied by v divided by, again I'm converting the summation to an integral. So 1 by 8 pi cube. 2 pi the whole cube is 8 pi cube. Uh, Integral of, this is just depend on k, the magnitude of k. So I can simply write 4 pi k square dk multiplied by h bar kfc minus h bar kc. So volume gets cancelled. 1 by 4 pi cube. The integral is even 4 pi gets cancelled. Okay, let's do that later. 4 pi. The first term will be this is just constants. Only k square dk has to be integrated. So it will become h bar kfc into k cube by 3 minus h bar c into this becomes k cube, this term becomes k cube, so after integration it becomes k raised to power 4 by 4. The integral is already done, so I'll just write the limits now. 0 to kf, because the summation was in energy values less than mu f, so the integral is from 0 to kf only. 4 1 by 4 pi square again. At 0 this value is 0, at kf this is kf, so this is just, I can take h bar c outside. Yes. Kf raised to the power 4 by 3 minus kf raised to the power 4 by 4. This is just h bar c upon 4 pi square. 1 by 3 minus 1 by 4 is 1 by 12, right? 4 minus 3, yeah, 1 by 12. So kf power 4 divided by 12. I know that kf rho is a function of kf cube. So here the pressure is a function of kf power 4. So then pressure has rho raised to the power of 4 by 3. So let me write this. Rho is a function of kf cube. Therefore, kf is of the order of rho raised to the power 1 by 3. Pressure is of the order of kf raised to the power 4. Therefore, pressure is of the order of rho raised to the power of 4 by 3. And that's the answer to my first question. The degeneracy pressure of an ultra-elliptic Fermi gas in 3 dimensions may be written as P, which is a function of rho raised to power n. What is the value of n? The value of n is 4 by 3. You can interrupt me anytime if you have any questions. Because I generally don't see much response, so I'll just move ahead with the next question, assuming that there is no doubt. If at all you have doubt, just interrupt me. Okay. So this is the second question. All right. So in this question, we are told to find the value of this quantity where u of xi obeys. Actually, I don't know what do you call this Greek letter. It's chi or xi something. What do you call this? Maybe I'll just call this chi. Chi chi. Let's call this chi. So where u of chi obeys Lan-Emden equation. All right. So what was the Lan-Emden equation, by the way? This was the equation, right? So I'll just copy this right here. What did I do? Why? Right. So this is called the Lane-Emden equation, right? I want to calculate a quantity which has this, and I want to, there will be a multiplication with chi and integrate this. That's what I want to calculate, right? So how do I do that? The trick seems to be this only, that here if I differentiate, if I take this derivative inside, so 1 by chi square, uh, the derivative will be with this chi square first and then with this, just multiplication tool of derivatives simply. Uh, what will be the result? First I'll differentiate this. So this will give me, the first term will give me 2 chi du by d chi. Sorry. Okay. So if I directly, so but if I do that, what will happen is minus u cube of chi into chi square and then d chi. This integral will have chi square du by d chi. I'll have it at limits from 0 to chi 1. Okay, okay, yeah, that also makes sense. Yes, similarly, yes, let's try that then. I've already tried the other method, I know it works, but let's try this one. This also seems fair enough. Okay, so let's do that. D by d chi of chi square du by d chi is equal to minus u cube chi into chi square. And now I want to integrate on both sides with d chi. Integrate with d chi. Okay, so what I'll get is chi square du by d chi. The integration runs from 0 to chi 1, right? Yes, is equal to minus of integral u cube. Acha, this I'll have to integrate by parts, na? Uh-huh. What? No, I did not understand what you're saying. Here, I do understand that this is the integral on the left hand side. The right hand side will have to manipulate this term somehow. But what is the suggestion? That's something I am not able to understand. Uh, okay. You're saying I'll just write chi into what can I write as u cube of chi? U cube of chi comes out to be from here. From here, I'll be writing negative of 1 over chi square d by d chi into chi square du by d chi. And I want to integrate this. Okay, so basically what I get. Okay, so now my integral, mm, will this be easier? Let's try, is equal to minus of, I will obviously integrate this term only. This term I'll be integrating. So in that case, I'll get 1 by chi into chi square du by d chi. This is from 0 to chi 1. U at chi du by d chi at chi 1. Okay, we do have that value. Minus integration will be, this will integrate, this will differentiate. So that will be 1 by plus, because minus 1 by chi square, that I differentiated. This I integrate chi square du by d chi d chi. This is the integration. 1 by chi square into chi square du by d chi. This will simply be, okay, cancel this out. I'll get u from, that's what you're saying, right? Okay, this seems fair enough. Minus 1 by chi1. Also, I have simply here chi1 minus chi1 du by d chi at chi1, right? And minus 0. Okay. And wait. What was this value though? Actually, no, I'll have to directly write this. Okay. U of chi1 minus u of 0. No, I guess that's the answer, right? U of chi1 minus u of 0, chi1 u prime at chi1. Yeah, that's the answer. We have it right there. I think we missed a negative sign somewhere, which we'll have to take care of course. But otherwise, that's the answer that we get. Yes, this is the exact expression with a negative sign outside. Yeah, so it can be done either way. Obviously, you can do a part integration, or you can substitute the u cube value. Either way, it just gives you the same thing. All that this requires is just integration by parts, and it can be solved very easily. Okay. Maybe I'll just check where I missed out the minus sign because this is not okay. So we substituted u cube. So what did we do by the way? We did kind of u cube kind. So I do have a minus sign here. Did I miss it out later? Um, oh, there was a minus. There was a minus coming from outside. There was minus because of the expression also. So there should have been a minus here. Is that what you're saying? So is this also? Yeah. Then we are done. Yes. It's not an overall negative sign. Yeah. Only here the minus sign is changing. So this was minus and this is plus. Right. Yes. So this is my answer. Yes. Right. The only mistake was that I had made a mistake here in writing negative sign. All right. All right. The next one. Okay. So this is the problem. We don't want the above one, right? Let's crop this a little bit. Yes. So this is your problem. I nu d nu is the energy density of radiation in a black body of temperature T between frequencies mu and mu plus d nu. Uh, okay. The value of integral mu into I nu d nu is what? That's what we're supposed to find out. Mm, here we have a direct expression of this, which obviously I'll have to refer. I don't remember the expression. Is it written somewhere? Where have I written it? So I nu is only this part. One I nu d nu is equal to 8 pi h nu cube by c square 1 by h t nu. This is what? Into nu. Here there's one more nu. So we'll just make this a fourth power now. Right? This is what we want to evaluate. Um, so what we are doing is we'll take h nu by t is equal to some x. So d nu is equal to x t by h. Okay. So nu I of nu d nu, this integral. That's what we want to evaluate, right? This integral becomes what? Xt by h comes from this nu. I nu has 8 pi h nu raised to the power of 4. So that will give me x4 t4 by h4 divided by c square, of course. Uh, d nu becomes into x t, actually d nu is dx, dx t divided by h. Sorry, I have multiplied with nu here. Now I'm doing d nu. Oh, I have multiplied here itself, so there won't be power. My bad, my bad, my bad. Yes, making some silly mistakes. Okay, q, right. Dx into t by h divided by e raised to the power of h nu, which is x minus 1. Okay, so basically what we get is, barring all the, we'll have t raised to the power 5. I'm just keeping whatever is important outside. Uh, nu I nu d nu, this integral is directly proportional to t raised to the power of 5. There are some constants, bunch of constants which you don't care about. And it has also, what is the power of x here? This is x raised to power 4 dx divided by e raised to power of x minus 1. So what this gives you, this is a standard form for, what is that function called? Arey, I forgot the name of the function. Just a moment. Riemann zeta function. It's called Riemann zeta function. I'm sorry. This is Riemann zeta function, basically xi of say chi or xi whatever of say s is equal to integral x raised to the power of s minus 1 upon e raised to the power of x minus 1 dx. This is the Riemann zeta function form, zeta function of s. So basically this is just directly proportional to t raised to the power of 5, and this integral will just give me this of 5. So the constants is just a bunch of constants which you can evaluate, but mainly the answer has to have this form, t raised to the power 5, Riemann zeta function of 5. So t raised to the power 5 are two options, but Riemann zeta function of 5 is this one. So this is my answer. I hope that's okay. Other all bunch of constants you can just get it. That's not a big deal. Okay, so next question is quite straightforward actually. Okay, so the question is, now if I double the frequency and double the temperature, the value of I nu becomes what? Again, we can see this expression of I nu here. Copy and put it there. This expression of I nu. Here, if I am doubling the frequency and I'm doubling the temperature also. So this nu goes to 2 nu. Here also nu goes to 2 nu. And T also goes to 2T. So let's just do it. Nu goes to 2 nu and T goes to 2T. So I of 2 nu will become, it also has temperature, 8 pi h 2 nu the whole cube by c square into 1 divided by e raised to power h into 2 nu divided by 2t. Temperature also is twice minus 1. This 2 gets cancelled, so basically temperature has no effect. But here the 2 is cubed, so I'll get 8 times I nu. So the value of I nu increases 8-fold. That is the final answer. This is quite a simple question. There is nothing to think about here. Just use the formula and get it. Uh, so a black hole has a temperature because this is just a theory question. If you've seen the lectures, it is this is just the answer. It's already here. It's already given, but you would know the answer if you've gone through the lectures. So it is exchanging energy with the surroundings and also has both entropy and internal energy. So that I'm not going to get into. And the last one is also quite straightforward. There is this direct expression there. Okay. So the time required for a black hole of the mass of a tennis ball. So tennis ball is just 50 grams they're taking to evaporate is approximately. Mm, so we have seen the dynamics, like the dynamics of how a black hole is evaporating. Sir has done that in the lectures. And finally, we had an expression of the form, I think, mass of T is equal to m0. Please correct me if I am wrong here. Divided by minus 3bt raised to the power of 1 by 3. This was the expression. So this is what we get finally. At time t, the mass, this is evaporating, the black hole is evaporating. Uh, the mass of the black hole at time t can be given by this m0, where m0 is the mass of the original star, and it's reducing in this manner. All right. So for it to completely evaporate, m0, basically this becomes 0. Mass of the star becomes 0. So m0 minus 3bt has to become equal to 0, so that the time for complete evaporation is m0 by 3b. That's it. Uh, so here sir had given one example. You can directly use that only. So we had, sorry, I'll take both of these values. Where is the q? m0 cube by minus divided by 3b. Okay. I don't remember this. Okay. The expression comes out to m0 cube by 3b. So maybe I'm maybe mistaken with this expression, but what I wanted to say was what. Give me a moment with this. Yeah, this was it, and this is it. Okay, so for sun, this time was given to be, if we calculate m0 cube, where m0 is the mass of the sun, m0 mass of sun and divided by 3b. This value for sun comes out to be 2.2 into 10 raised to the power of 74 to 2.2 into 10 raised to the power 74 seconds. For sun, this is the value it comes out to be. M0 for sun, the mass of sun basically is 2 into 10 raised to the power of 30 kgs. So now what we can do is, I know the value of m0 cube by 3b. What I want is the time required for the small ball of mass small m to evaporate. So I can just simply do this. M0 cube by 3b is just this 2.2 into 10 raised to the power 74 seconds. I will divide it by m0 cube, the mass of sun, and multiply it by m cube, which is mass of the ball, the small ball. So this is just 2.2 into 10 raised to the power 74 seconds divided by what is the mass of the sun? The mass of the sun is 2 into 10 raised to the power of 30 kgs, which is your kg cube here, the whole cube, multiplied by the small mass. The mass of the tennis ball is 50 grams. So 50 into 10 raised to the power minus 3, the whole cube. So 2.2 10 raised to the power 74 seconds divided by 8 into 10 raised to the power 90 kg cube. This is also kg cube actually. So this kg cube goes away into 5 into 10 to the power minus 2, which is 5 cube 125 into 10 raised to the power minus 6 kg cube. So the powers are basically 74 minus 90 minus 6. What do we get here? 74 minus 90 is minus 16. So minus 22. So 2.2 into 125 divided by 8 into 10 raised to the power of minus 22 seconds. So you have to just calculate this number. And we have just this one answer. It's minus 21, close to it. So this would be the answer. Mhm. What's the answer for this? Am I doing it wrong? Oh, it is this. Yeah. Uh-huh. Yeah, we can of course do it directly. I did not want to use the expression of b and everything. This was because we already know the value. Like I was just seeing the lecture and we know the value of this, so we can directly use it. But yeah, fundamentally you should actually be using the expression for b and calculating this. Yes. So that's it with tutorial 4. Any doubts with this? All right. So from next week, like my regular sessions are on Mondays only. So from next week I'll be starting like week 5, week 6. It will be regular from Mondays, 7 to 9 p.m. So yeah, you guys can join if you like. Okay. Thank you.